Let's take a few minutes to discuss how we use this melting point data table. You want to include a table like this in every notebook entry wherever we're going to take melting ranges, and we typically take the melting range of a compound after we've isolated it, say from the recrystallization that we did earlier in the semester, or we've isolated it from maybe a liquid-liquid separation that we're going to do in a few weeks. And we use the melting point or the melting range of the compound, and we'll probably use those terms interchangeably. It is a range technically, but we sometimes call it the melting point. But we use that to get an idea of the purity of the compound. If the melting range of our compound matches what people have reported in the literature, then we probably have a very pure compound. If we're slightly lower, then we might have some impurities. If we're very much lower, then we probably have a significant amount of impurities. So let's look at this melting point table. The first thing we need to do is look up the literature values of both the compound we're studying, acetoanilide, and the standard that we're going to use, benzamide. And we can find those on the internet or in other chemical references. It's easiest these days to use the internet. Aldrich.com is a website where you can buy chemicals, or I should say laboratories can buy chemicals, and they often will have the physical properties of those chemicals a little bit further down on the page. So if you go to aldrich.com and you look up benzamide, there's probably several different size of bottles that you could buy, maybe a 5-gram bottle and a 100-gram bottle and maybe a 500-gram bottle. But if you scroll that page, at the bottom you should find some physical properties, and those include melting range, maybe boiling point, most likely molecular weight or molar mass, and density. In this case, we want to find the melting range. You could also use a website like ChemSpider, which I believe is sponsored by the British government, and you could also use Wikipedia. If you're worried about reputation of websites, look at 2 different websites and see if they come up with the same value for these melting ranges. And if you find the same value, oftentimes you're probably on the right track. Also, when you get to lab, you'll see that our standards, which are in small vials, will have the melting range listed on the side of them. So you can get the melting range from that. While I'm on the subject of standards, the appendix file that we showed you at the beginning of the semester has a list of about 10 melting point standards that our stockroom has for you. Eventually, we're going to want you to choose your own standard. And we'll choose a standard based on how close its melting point is to our compound's expected melting point. And you can always go to the stockroom and ask for a standard if you want to. So if you look at the vial of benzamide when you get to the laboratory, you'll find that it has a 125 to 128 melting range. And if we look up acetoanilide from Aldrich or Wikipedia, we'll find 113 to 115 is the melting range for acetoanilide. And if you want to put it up here too, that's fine. It's the same compound there. We just have it grayed out because we don't really need it twice. And so those are the numbers that you should have before you get to class, before you get to the lab. And you can do that every time we're about to set up a melting point experiment. So I'm going to put in some fake data now, and we'll talk about how to come up with a correction factor and what information we can actually glean from this melting point, melting table. So let me just add some numbers here. Probably these are different from yours or what you'll acquire in lab. All right, so we've done the melting point experiment. We've put 3 different tubes in the Digimelt, which you'll see in person. We found these numbers, and now our goal is to come up with one number that corrects the standards values to as close as we can without going over to the standards literature values. So what is one number do you think that you could add or subtract to the standards numbers to get it as close as possible to the literature? Now I hope you came up with +3. And that's going to be the same correction factor that we use for all 6 of these, but we get that correction factor by looking at the standard and comparing it to its expected literature values. And then we're going to add 3 to each number here, 124, 128. You can see how I corrected it. The upper bound I corrected to 128. The lower bound is a little lower, and that happens sometimes. But we really don't want to go over the literature value because it's very unlikely that any solid would melt at a higher temperature than we expect it to melt at when it's 100% pure. There's no way that a solid could be 110% pure or 120% pure, so it really makes no sense that any melting range would be beyond the upper bounds of the literature value. So I'm going to take that same +3 and I'm going to add it to every other number that I acquired on this same melt temp experiment. And then I'm going to observe basically inside this red box. Those are the numbers that are useful to me in my discussion or reporting my final results. Okay, so you're going to have this table in your results section of a report. You're going to have this table in maybe a results section of your post-lab worksheet. So everything in here gets reported in your worksheet or your report. But when it comes time to discuss your results and draw conclusions from them, really we're only going to look in that red box. We're going to say the corrected melting range of my recrystallized acetoanilide was 112 to 114, and then we'll compare that to what we expect from the literature range, and you can see that I'm just 1 degree off. So this is very close to pure acetoanilide. I think in this case, we did a good job of purifying the acetoanilide, and I have no complaints about this 112 to 114 range. Now, it's not often that we're going to intentionally put impure sample into the melt temp because we expect that to melt lower and broader, and indeed we saw that here. 103 to 114, that's kind of like where we started before we tried to purify the acetoanilide, and now we've been able to raise the lower bound of the melting range and get it to be significantly more narrow, and that's exactly the goal. So this tells me that we have done a good job purifying the impure acetoanilide with our recrystallization technique. So that's the conclusions we'll draw from here, and we'll really only use these numbers. We don't even really report the correction factor once we're beyond the results section of our report. In the discussion, we just say the corrected melting range was 112 to 114. So I'm going to erase this now and come up with some alternative numbers, and we'll talk about what we might do in that case. Of course, the literature values stay the same, so I'm going to leave those there. And what if we have some alternative numbers here? I'm not going to worry about the impure acetoanilide. We've talked about that. So now think about what correction factor you would use to correct your standard to be as close as possible without going over to the literature values. And in this case, +1 works great. Both of those numbers will get corrected to be exactly what we want. I will point out here that you can use negative numbers for the correction factor. You can use 0. Our Digimelts will often give you the temperature in a decimal, so it might be 124.3. You can certainly write those down on your melting range table, and you can use decimals in your correction factor. So if you wanted to correct by +1.6, you can certainly do that. If you want to correct by -0.4, you can do that as well. So I'll add 1 to my 102 and 107. And what would we conclude now from our recrystallized acetoanilide? I hope you recognize that these numbers are much lower and a little more broad than what the literature is. So this acetoanilide on this second demo numbers is much less pure than the first one. It still was a little bit more pure than where we started, but in this case, we might conclude we didn't do such a good job with the recrystallization, and it might warrant a second try at the recrystallization. We might want to do a second recrystallization. And I want to do one more set of fake numbers. In this case, let's see if we do this. What would the correction factor be in this case? I think in this case, +3 would be our correction factor. We'd correct the 125 to 128, and the 115 to 118. And then I can do the acetoannulid. You can see here we've had a very broad range for our standard. Now the standard is assumed to be pure. You can actually buy solids that are highly purified to be used as melting point standards, and so there's really no reason for your standard to ever have this great of a range. And so in this case, this is an indication that you might start over, right? Your experiment didn't go as you expected, and that's kind of why we have the standard. This is the control in our experiment. We know where it should melt, and so if it melts in that range, we know that the experiment went as expected and that the data we got from our own sample is probably accurate. In this case, something happened. Maybe we heated the samples too fast, because sometimes you can have too high of a ramp rate on your Digimelt, and in that case, the thermometer might not be reading exactly what the sample is experiencing inside the heat block at any one time, so that might give you some inaccurate numbers, or something else could have happened that just causes us to disbelieve this data here. So in this case, we would want to start over. And the Digimelts really don't take that long to do a melt temp experiment, so starting over is not a terrible thing. In fact, you'll have plenty of time to do an extra round of melting if you need to during this lab period. So that's what we use the standard for. It's the control. It tells us that everything went as expected and that the numbers that we got from our acetoannulid, which we didn't know what to expect because we didn't know if it was pure or not pure, tells us that these are correct numbers, or as in this case, I don't believe these numbers. So I'm going to make a new table. I'm going to get a new sample of benzamide, new impure acetoannulid sample, new recrystallized acetoannulid sample, and I'm going to start over and do this again. And in theory, our benzamide should start to look more like what we saw in the first two demonstrations of this melting range table. One last thing I want to point out, the correction factor is always applied to every number that you obtained during that same melting range experiment. You would not use the correction factor that you used a few minutes ago or the correction factor that you used last week. You always obtain your own new correction factor based on the standards. You always will have a standard, and that correction factor will be applied to everything. Some students get the mistaken impression that, you know, I got my acetoannulid numbers here, I want to correct those as well. So I'm going to add 10 to my first one, and I'm going to add 12 to my second one, and hey, look at that. Now those red numbers look great, right? I just corrected them to be exactly what we'd expect from the literature. But my question to you is, if you're going to do that, why did you bother to stick this sample in the melt temp? Just write down these numbers, because you're going to correct them to these numbers anyways. So that's not the proper way to do a correction. We want to use the standard and the difference between the standard and its literature value to come up with a correction factor that basically calibrates all of the numbers that we obtained during that melting point experiment.